Hi, everyone. So at this point in the class, you probably have the impression that the subject of relativity is about these weird effects, length contraction, time dilation. And perhaps you think that what the subject is about, it's really about transforming, time interval from one frame to another, space interval from one frame to another. And today, I'm going to try to pivot your understanding of the subject from thinking that it's about transforming from one frame to another to two broader ideas, bigger ideas, right? So we've been seeing the trees. Now we're going to try to step back and see the forest. The first of these ideas is that space and time are interrelated. They're interconnected. You can still talk about spatial aspects and temporal aspects, but really these things are interweaved together. And the second subject that we will see in the next video is that while the spatial interval between the two events has a different value in another frame, and while temporal intervals has a different value in another, and while something that looks like just an interval of space becomes an intermixing of an interval of space and time in another frame, and vice versa, while all these confusing effects are taking place, in the midst of all this, there actually exists a quantity that is invariant from one frame to another. There exists a quantity that takes on the same value in all the frames. And so relativity is not really about how to relate intervals of space in one frame to intervals of space and time in another. But the heart of it is that there actually is a quantity that's invariant. And I heard somewhere that Einstein originally wanted to call it theory of invariance. It's that the key is not that some things change, but that amidst all these changes, there is a quantity that does not change, and that's the brouhaha. So let's build up to that. So first, like I said, let's examine interrelatedness between space and time. And we've already seen this interrelatedness in many physical ways. Perhaps the most direct way to see it is just by writing down Lorentz transformations. So let's consider this scenario. There's event 1 and event 2. Okay, so I'm in my room. I'm observing two events, event 1 and event 2. What I just showed you is a pair of events that are separated by delta x and some delta t. So in my frame, the two events are separated by some interval of space. They take place at two different coordinates and some interval of time. And we can use Lorentz transformations in the interval form to relate the interval of space and time in my frame to interval of space and time in another, right? So recall that we have delta x prime, some other frame, s prime, equals gamma delta x minus v delta t. And delta t prime equals gamma minus v over c squared delta x plus delta t. So let's look at two special cases. The first special case is when both events took place simultaneously in my frame. So case 1, delta t equals 0, i.e. in frame S, the two events are separated only by space, but not by time. According to Lorentz transformations in frame S prime, well, they will be separated by a different amount of space. But notice that the point I'm trying to make is that they're also separated by a time interval. And if speed is much less than speed of light, that time interval is not very great. But the point is that delta t prime is not equal to 0. So while delta t equals 0 in one frame, it's not 0 in another. They're separated by a combination of space and time in frame S prime. Time measured in frame S prime. Case 2. So case 1 is events are separated only by space. Case 2 is events are separated only by time. Okay. Events. So let me do this. Delta x equals 0. So in frame S. And again, let's see what happens in frame S prime. Well, delta x prime equals minus gamma v delta t, and delta t prime equals gamma delta t. So again, in frame S prime, the same two events are separated by space and time. You see what's going on here? And in general, if in frame S they're separated by some delta x and some delta t, and as you can see from Lorentz transformations, in frame S prime, they're separated by a different amount of delta x, or delta x prime, and different amount of delta t prime. And so the spatial separation in frame S prime intermixes spatial and temporal separation in S. And the temporal separation in frame S prime intermixes spatial and temporal separation in frame S. So we have intermixing. What's given by the pair of events that are separated by some amount of space and some amount of time in one frame are separated by a different amount of space and different amount of time in another frame, where you have this kind of intermixing. The delta x in frame S prime depends on both delta x and delta t in frame S. Well, that's actually true even in Galilean relativity, right? So the first equation looks the same except for the gamma factor. But the second equation really is is new, right? In Galilean relativity, delta t prime equals delta t by assumption. In special relativity, we see that that's not true. And moreover, delta t prime depends both on delta t and delta x in the other frame. So the second equation is just, in words, it would say that there's no such thing as universal time. There's personal time. You know, the time of a given frame, right? And the same can be said of space, right? There's no such thing as universal space. There's personal space, right? All we have is rulers and clocks. We have frame 1, it has its rulers and clocks, and frame 2, it has its rulers and clocks. And we relate the reading on rulers and clocks from one frame to another frame. But the big picture, the big takeaway from this is that what is just the interval of space in one frame is a mixture of space and time in another, and vice versa. So where am I going with this? This suggests that perhaps it's not right to talk of space and time. They're kind of intermixed. First of all, there's personal space and personal time. Time is not universal, right? Time flows at different rates in different frames. And second, you can see, because of this intermixing, maybe we should talk of a single entity, and that single entity is called space-time, just one word with no dash, right? So instead of talking of space and time, we should talk about space-time. It's like a two-variable space with two variables, space and time. So to explore this object called space-time, we're going to draw these two axes, the space and time axes. And for some reason in special relativity, the time is drawn on the vertical axis. Let me try to make this bigger because we're going to need more. Just a second. Now I could call this x-axis and I could call this time axis, but by convention, I'm going to make the vertical axis not time, but time times c. And the reason for that is, if we deal with large velocities, instead of slopes being 1/c, the slopes would be like 1, right? If we deal with light, right? In this space, light follows a trajectory with slope 1. But if we didn't plot CT, if we looked at the axis t versus x, then light would have a slope of 1/c, and it's a very, very small slope. You can also think of c, the reason that c gets tagged along is that we're just using bad units. Instead of meters for x coordinates, we used light seconds, the distance that light travels in a second. Then speed of light would be 1 light second per second. C would be just naturally 1. And then we wouldn't need to stick the c along with t. But because we're using units of meters, they're not units based on how fast light travels. It is convenient to plot ct versus x rather than t versus x. So now let's consider an event. And let's say that this event in some frame takes place at x equals 0, t equals 0. Okay, so some kind of an event that takes place at x equals 0, t equals 0. I could just define the origin of my spacetime based on that event. First, let's say I shoot two beams of light, one in the right, one towards the positive x-axis, the other towards the negative x-axis. On this space-time diagram, so I'm kind of laying out the language of space-time for now. And this is like a map of space-time, right? So I'm shooting two beams of light. This one will have a positive slope. This one would have a negative slope. And so this is, these are, they form a triangle, but this is called a light cone. And the reason it's called a light cone is that if I worked in not one dimension, but for example, 2 dimensions, so 2 spatial, so X and Y, and then CT here, then instead of just 2 beams of light, you know, I could shoot light in this direction, this direction, this direction, and this direction. And if you add the temporal axis, then all these beams of light, they would form a cone. Again, it is, the CT is like a 3rd dimension, but it's not a spatial dimension. You see both X and Y, they're spatial coordinates, but time is a temporal coordinates. So it is a 3rd coordinate, but it's a coordinate of a slightly, it's distinct from spatial coordinates. Yes, space and time does get intermixed, but still temporal coordinate has its own property and spatial coordinates have their own property. So this is why it's called the light cone. In one dimension, one spatial dimension, it doesn't form a cone, it's called a triangle, but the name still sticks, cone. And similarly, you could have 2 beams of light that are moving towards x equals 0 that happen to arrive to that point at t equals 0, right? So you see there's 2 beams of light, and this is in the past. So first of all, while I'm at it, I want to make it clear that while space-time is like a 2-dimensional superspace, it is not a space like a physical space. It's a space of events. So any point in this plane, in the plane of space-time, is an event. This is an event. This is an event. This is an event. This is an event. So space-time is a space of events. If the word space confuses you because when you think of space, you think of like physical space, you know, that away, or that away, then just replace it by set of events. Space-time is a set of events. Space-time is a set of events. So let's continue exploring features of space-time. Now, let's say, so since I drew a couple of events, actually I like this. Let me call this event 1 and event 2. Is there a way that this event at the origin, is it possible for it to influence event 1? In other words, can this event at the origin be the cause for E1? Pause and think about it. Well, let's see. The answer is no. There is not a signal in the world that can reach this location in this amount of time. You see, E1 is removed from the event at the origin by too much space and too little time. So we would say that E1 is causally disconnected from the event at the origin. But it's really just a fancy term for a fancy way of saying that there is no way that information can reach this distance in this amount of time. It's too far with too little time in between them. So E1 is not causally related to E2, to the origin. But E2 can be causally related, right? I can send, for example, a signal that travels slower than light, and it can reach this location in this time. there is enough time given the space. So for example, this could be maybe an electrical signal. How fast electrical signals travel? Not quite at the speed of light, but like a good fraction of the speed of light. So this could be electrical signal. So you can see that everything that lies within the light cone is causally connected to the event of the origin. And everything that lies outside of the light cone is causally disconnected. So let me try to find a good color. I'm going to use blue. Right, so this set of blue events, I'm not sure if it comes out as blue on your screen. The set of all events that can be causally connected to event at the origin is called particles future. So why particle? Let's say there's a particle, right? Let's say a particle, let's say I'm describing the fate of the particle. So at t equals 0, the particle is at x equals 0. That's why the word particle came in here. I guess I should have said that earlier. I just said that it's an event. Now let's say it's a particle that moves through space as time evolves. So this particle's trajectory could be something like this. So this is a particle's trajectory through space-time. But again, remember, space-time is really a set of events. What this means is that at this time, the particle will be here. At this time, the particle will be here. At this time, the particle will be here. So it's a series of events. Events that mark the location of the particle at different instants of time. So this is particle's trajectory. And in the past, the particle was also somewhere, right? So this is particle's past. And particle's past that lies within the light cone is a set of all events that could have influenced particle at t equals 0. So particle's past is a set of all events that could have influenced particle at t equals 0, and particle's future is a set of all events that a particle can influence. For example, it can arrive here. Or, for example, if it followed a different path, it could arrive here. But it could not arrive here because it's too far given the little amount of time. I'm really not saying anything that you didn't already know, right? So you already knew that speed of light is the maximal speed. And this is just a fancy way of representing that. But it is useful to know that space-time can be segmented into these causally connected regions and causally disconnected regions. Now, a trajectory of particle through space-time is called particle's world line. World line. Really, these are all things that you could have known since 5th grade. I don't know, it's just, we're putting fancy words on all this. Okay, and for some reason your textbook calls it absolute past and absolute future. I'm not sure why they use that language, absolute past and absolute future. In any case, the particle's past is a set of events that could have been the causes of event at the origin. Or you could say that this is a set of events that could have influenced the state of the particle at t equals 0. And the particle's future is a set of all effects of event at the origin. Or you could say that this is a set of all events that particle at t equals 0 can influence in the future. Your textbook calls everything else, it calls it absolute elsewhere. In other words, these are events that are causally disconnected, right? So I should use a gray region maybe. Not sure if gray will come out really well. So let me use maybe a pencil. Pencil. So this is causally disconnected. parts of space-time. So anyway, so this is the dissection of space-time, and it will be a useful language for as we move on. So in summary, space and time become intermixed when you go from one frame to another. So therefore, it's useful to talk of one object, space-time. When we talk about space-time, this is a vocabulary that's useful in discussing space-time. Space-time, it's like this two-dimensional space, but it's really a space of events, a two-dimensional plane where a point on that plane corresponds to an event. You can also discuss trajectories of particles moving through space and through time, or through space-time, where each point on that trajectory is an event, and the particle's trajectory through space-time is called a particle's world line. Notice that the slope of the particle is always bigger than 1. You can never travel faster than speed of light. Instantaneous speed cannot be faster than 1. But since time is on the vertical axis, the slope is always greater than 1. So in the next video, we will look at the second effect. Like I said, not the second effect, but the second topic. Like I said, I want to pivot your thinking from relativity as this just about transformations to relativity being a theory about a relationship between space and time. That's really what it's about. It's a theory about relationship between space and time. So first, I introduced the notion of space-time as a single object, and we will come back to it. But second, the fact that space and time are kind of interrelated will become even more clear when we look at the next topic in the next video. And that will be invariance of a space-time interval. So while delta x transforms into delta x prime, while the delta t transforms into delta t prime, while all these things are changing, it turns out there exists a very, very special quantity that goes by the name of space-time interval, and that quantity is invariant. And when we stare at that quantity, we will see, when we stare at it long enough, we will realize that this quantity has a geometric meaning. And in the third part of today's lecture, which is optional, third part is optional, but I think physics majors should watch it. We will talk about the geometric meaning of this quantity called space-time interval. And we will come to a conclusion that space-time is not just a two-dimensional plane, but we can talk of geometry of space-time. Space-time comes endowed with a certain geometry. And that's the subject of the third video. So all of these videos pivot you away from thinking of relativity as just a weird set of transformations that are a headache. I mean, Galilean transformations can already be a little tricky. But these are a total headache. Trying to pivot you from that viewpoint to realizing that really relativity is about studying interrelatedness between space and time, and ultimately the geometry of this object called space-time. Again, part 3 is optional. I hope you will watch it, especially if you're a physics major. But if you're struggling with the class, you can skip it. Then maybe some other day you will come back to it, or maybe not come back to it. So, okay, good. I'll see you in the next video. The next video will be edited from last quarter, so I will cut a piece and I will try to make that transition as smooth as possible. Maybe I'll have to write a little comment to explain what's going on, but I think you will figure it out. Okay, thanks, bye.